Okay, so now I'm going to summarize what you just saw in some of those Khan Academy videos, which is the physical interpretation of the curl. And it's measuring what I'm calling the microscopic rotation or circulation of the vector field. And what I'm meaning by microscopic as opposed to macroscopic. Let's look at another demo I really enjoy. This is from Math Insight, the website Math Insight. And here, kind of similar to the Khan Academy, we're using this idea of like a spinning sphere. But in this first example, we're not pinning it down. So the fact that these spheres are rotating in this example is not capturing actually what curl is measuring. Curl is measuring, this is what I call macroscopic rotation here. Curl is measuring this, what we call microscopic. So really we imagine that we are pinning it down and then we see would it rotate. And as we would expect, even when we pin it down, we still get this counterclockwise rotation. So the curl in this vector field, actually at any point, is going to be this three-dimensional vector. It's coming out of the xy plane at us because of the right-hand rule. And you can see a little bit, that should look like a little 3D vector. I think it's hard to see in the angle. Oh, there we go. There it is. Okay, cool. So no matter where we are in this vector field, the curl is always the same vector because I get the same microscopic rotation. Okay, now we're going to be working with nice vector fields like this, where what happens macroscopically is consistent with what happens microscopically. However, I want to point out to you, there's some vector fields where this doesn't hold, and that's why one of the theorems we're about to prove is going to require that we work in these nicer vector fields and not the ones I'm about to show you. So let's look at what happens. This is an interesting one. Again, I have macroscopic rotation here if I just let my spheres and the little ball flow. But now if I pin it down in this particular vector field, and I think I can pull up, yeah, what the vector field is for you here. So I'm pinning it down, and this vector field is listed here. This is not an error on the applet. These are actually not rotating anymore. And you may be saying, wait, how is that possible? But I want you to notice something. My vectors are longer down here, which means that the velocity of the fluid is faster. So it's pushing it harder down near the bottom. And typically, if I had more like faster fluid pushing from the bottom, I would actually want to induce clockwise rotation, right? Because I have faster fluid hitting than right here. But then I also have this counterclockwise force from the fact that the vectors are pointing in general counterclockwise. And so it happens to be that those two forces exactly balance each other out. And that's not at all obvious from the picture. One thing that you can notice about this particular vector field is that it's not defined at the origin. And that's going to be something that will be a red flag to us when we're trying to use curl in our theorems later in this class. If our vector field is not continuous within our region, or if its partial derivatives are not continuous within our region, then we won't be able to use the curl to tell us about how things are circulating. We won't be able to use the Green's theorem and Stokes' theorem because of this exact situation where what happens macroscopically doesn't match when you get to the microscopic level. And there's a couple other like that break down. Let me show you a couple other ones. Here's another one that breaks down. Again, it's not defined at the origin, and that's what's going to cause some of this. It's going to be a hint to us that we're going to have an issue. Here I have, it looks like macroscopically, if we let this stuff go, it would definitely rotate counterclockwise. But actually, when I pin it down, I'm getting clockwise rotation. And that's because you notice these vectors down in the bottom are much longer than the vectors on the top. And so they're pushing a lot faster than those vectors. And it's enough to actually counterbalance and make this rotate clockwise. And it's not the same everywhere in the vector field. If you notice, as I move it around, I'm going to get different rates of rotation, which is what you're seeing by longer and shorter curl vectors on the left. Okay, so again, the curl is defined. This vector is defined. It's not defined at the origin, but what we're going to use the curl for in this class is going to be to help us figure out how things are circulating around curves. And so in this case, this vector field will not hit the criteria that we need to have continuous partial derivatives everywhere inside our region. And that's kind of what's summarized here if you want to read this. It's saying, shouldn't there be a relationship between macroscopic and microscopic? And the answer is yes, in general, that should be the case. But it really only works if we have functions that are continuous and whose partial derivatives are continuous. And that's going to be the requirement for what we call Stokes and Greens. And then lastly, I want to point out, so this is a vector field that does satisfy the requirements. It is continuous and its partial derivatives are continuous. But when you look at it, it doesn't necessarily scream out to you that you have rotation happening. And the reason that you can see we do get spinning is because, again, my vectors are going faster up here than down here. So that if you think of it as water, the water's zooming a lot faster by on this side than down here. And so if you stuck a little paddle wheel into your river, it would in fact rotate. And this time I'm going to get clockwise rotation, so my curl vector is pointing downwards. So this is a vector field that we would be able to use with Green's or Stokes' theorem, which we're about to prove. But again, it doesn't necessarily scream out to you rotation until you look carefully at this. Okay, so let's go back to our handout. Okay, and just to summarize what the past few videos have been showing, the direction of the curl is going to be giving you the axis that this fluid would be rotating around. And we're thinking of it rotating either around a fixed sphere or a fixed paddle wheel. I'm just going to call it a fixed paddle wheel here. And by a paddle wheel, I'm just meaning this kind of picture right here where you are pinning it down at the center. And then the magnitude of your covector is giving you an indication of how fast the fluid's rotating. So let's practice just finding it for these three vector fields that I have. I plotted the first two. The third one is three-dimensional, so I didn't plot that one. So go ahead, put it on pause, and just practice calculating the curl for all three of these. Okay, and so one of the things I want you to notice about these first two examples is our curl can only have a k component in these first two examples because it's two-dimensional vector fields. And so the only option for a paddle wheel to rotate is either going to be around the positive z-axis or the negative. So that's always a nice shortcut when you have two-dimensional vector fields. One of the things to notice also is that we only defined curl in terms of three-dimensional vectors. So if you have a two-dimensional vector, you're still doing a 3x3 determinant, and you're just letting this k component be 0. Okay, so in my first case, I get this 2k hat, which again is helping me picture that at any point in this vector field, I have a vector pointing out in the k direction. It has the same magnitude at any point. It's a magnitude of 2. And there's actually a really great interpretation of this. I'm going to jump over to it for a minute.
If we take a look at this vector field here, if we look in the center, this is kind of the clear-cut whirlpool counterclockwise rotation example. And if we play the fluid flow, the fluid does indeed rotate counterclockwise in the region. But contrast that with what goes on over here on the right. This doesn't look like rotation in that sense at all. Instead, the fluid particles are just kind of rushing up through it. But in fact, the curl in this region is going to be just as strong as it is over here. And I'll show that with the formula. I'm kind of computing it through in just a moment. But the image that you might have in your mind is to imagine a paddle wheel of sorts, where let's say it's got arms kind of like that, and then you hold down with your thumb that middle portion. So even though the paddle wheel left to its own devices would just kind of fly up, I want to say, let's say you're holding that down with your thumb, but it's free to rotate. Then the vectors on its left are pointing up, but less strongly than the vectors on its right, which are even greater. So if you imagine that setup and you kind of have your paddle wheel there, then when you play the fluid rotation, holding your thumb down, but letting the paddle wheel rotate freely, it's also going to rotate just as it would over here in the easier to see whirlpool example.
And so that's really what we found with this example here, where our curl is the exact same vector no matter where we are in this vector field, because no matter where we pin down the paddle wheel, we will get the same speed of rotation in the same direction. We can contrast that with what happens to this vector field here, which is this one that points radially outward. And notice if I were to put a paddle wheel down at any point here, the way the vectors are hitting my paddle wheel, I'm going to get an exact equal force on either side such that I don't get any rotation, or an exact equal push of the water at any given point. So I don't end up with any rotation. And we can see that just by calculating this algebraically here, where I get 0I minus 0J plus 0K. So this is a vector field that has zero curl everywhere. And we have a name for that. In general, if a vector field has zero curl at all points, it's called irrotational. Okay, and then lastly, we have this 3D vector field, which we can just calculate the curl. And so for this one, we should have gotten negative y for the I component minus j. My j component's going to be 0 plus k, which is going to be negative x.